Okay, what we're going to talk about today is the half-lives of the decay process, okay? Some compounds will decay, like if you have 5 grams in a minute, you'll have 2.5 grams. And then a minute after that, you'll have 1.25, and it'll keep getting smaller and smaller and smaller. Some of them, it's thousands of years between when if you start at 5 grams, where you'll have 2.5 grams left. So it's a crazy, it just depends on the element, how long it takes for it to break down. Now, is that a big deal? Well, they use carbon 14. If you've ever heard of radiometric dating, they use carbon 14's half-life to figure out the age of a lot of like fossils and things like that. We have nuclear waste from power plants, plutonium. It takes forever, years and years and years, thousands of years for that to break down. So that's an issue. They can use it in like medicine. There's all kinds of things where they have to determine. But if you look here, it's kind of a crazy number. But again, I'll show you how to figure it out. But the half-life is a process, okay? It's the time required for half of the radionucleotide sample to decay. And they have some here, some half-lives. You can see down here, like carbon 14, when I was talking about. It takes 5,700 years. That's its half-life for it to break down in half. And it's a beta decay, which means it's an electron. You have some alpha ones up here, uranium. And again, here's where you're going to have some issues with long. I mean, look how many years that is. There's some synthetic ones. You can see here's iodine. And again, this is something they use a lot in medicine. 0.022. So, it doesn't take very long for it to break down. And again, it's a beta, which would be an electron. So you can see these are some examples of half-lives. Okay. And again, like I was talking about, they use radiometric dating. The first order kinetics, the half-life information that you'll see is what they call a nuclear clock. It goes through it there with Mr. Giraffe, and when he dies, and then his skeleton, and when they go through, but they can figure out the age of things by using carbon 14. The half-life of carbon 14 is 5,700 years. Okay, so it's limited to objects that are about 50,000 years old because of that long half-life. But again, they use it. They use how much is left. They know how much should be there. They look at how much is there, and then they compare how much has decayed, and they can determine how old things are. So the most common way to date, like I said, fossils, anything found in the fossil record, they use carbon 14 dating. But again, it has to be at least 50,000 years old for it to work, I guess. Okay. Other isotopes that they can use, they find in rock. There's uranium-238. There's lead-206, which you find in rocks. But again, pretty much carbon 14 is the way they date fossils. Okay. What they do is they look for activity in radioactive activity. They have units used to measure activity as follows. So when we're looking at radioactivity, okay, it can be a good thing and it can be a bad thing. So it needs to be measured. They have the becquerel. It's 1 disintegration per second. Okay, they use it as BQ. The Curare, named after Marie Curare, because she's the one that really worked with a lot of radioactive. Unfortunately, it gave her cancer and took her life. Excuse me. She worked with radium a lot, and so she determined that 1 gram of radium disintegrates 3.7 times 10 to the 10th per second. So these are things that disintegrate very fastly. It depends on what you're using, which unit you would use. Ways they measure radioactivity, and I think the most common actually is the curarium or whatever, Marie Curare's way of measuring. But if you work around radioactivity, you could wear a film badge. They have Geiger counters. I'm sure you've seen them. Those little things that go like that. There's actually something called phosphorus. It's a counter similar to a film badge, but it's made a little bit different. And what they do with the film badge is, okay, if you work like in a medical field, okay, and the reason why one of the units of radioactivity is the the BC or the BK, the guy that figured it out, Henri, not Henry, mind you, Henri Becquerel, what he saw is it fogged up a photographic plate so you could actually measure that. Okay. When the film has been exposed or used to detect radioactivity, okay, it means darker spots. So what if you worked in like a lab, an X-ray lab, or where you have radioactivity, you'd wear your little badge, and at the end of the day, they check to see where you're at, and you can see it's white before exposure in the middle. Okay, and these are the measurements on the sides. But if it's really dark like that, you've been exposed to a lot of radiation. You'll probably be taking a little break. You know what I'm saying? But this is ideal. But if you've been exposed to radiation, you'll see this. These can be used in obviously you can see she's wearing a white coat, so it's probably someone in the medical field. They also use them in like a nuclear power plants. Anytime you're on nuclear, you can use them. Okay, so film badges are used by people who work with radioactivity to measure their exposure over time. And again, it's to double check to make sure they aren't getting exposed, because if that is, then they got to look at what they're doing, the procedures and so on, and then probably give them some time off because they might have some issues. Okay, the Geiger counter, like I said, is kind of a machine. It measures the amount of activity of a sample. So you hold it over a sample and it goes, it just amplifies the current that's set off. It has a high voltage thing, and it just amplifies it so you can see it. It will determine radiation, alpha, beta, or X-rays. So it's not specific. It'll tell you all kinds. So it's kind of nice in that sense that it'll give you all the numbers. The radioactivity, like I said, enters the window on the end, and it creates ions in a gas. The ions result in an electric current. Because again, ions is charged particles. So an electric current that would be measured and recorded by the instrument. And you can also hear it. And the faster it's going, the excuse me, the more amount there is. Now you have to measure what kind it is, because if it's an alpha, that's not a big deal. If it's a beta, it's going to be harder. If it's gamma, it's going to be, could be life-threatening. So you have to look and see, but the machine will read all of them. Then we said phosphors. It's there's a substance, a radioactive, or some substances absorb radioactivity, and then they emit light. Okay, phosphors is one. There's an instrument used to measure the amount of light emitted by, they call it I got to remember this, secantillation counter. Sorry, these aren't stuff I work with all the time, so I'm not very good at them. But anyway, it converts the light to an electronic response for measurement. A spectrophotometer works like that. Stuff comes in and it takes the amount and it changes it to electric current, so then you can read it. So it's going to convert light to an electronic response so that you can actually measure it. Okay, so again, it's going to be a substance that absorbs radioactivity and emits light. That's the only way it can work. So the thing comes in, hits this substance, whatever it is, and it's changed to light, and then the light can be read by the machine. We also have what they call radio tracers. Okay, radio tracers are used to study a chemical reaction. Okay, they use radio tracers in medicine. I don't know if any of you guys have had to have certain tests or stuff. They make you drink some stuff beforehand. They're going to go in and they're going to get involved in a reaction, and they're going to look. Iodine is one that's very common if you have thyroid issues and stuff like that. But anyway, an element can be found through a reaction to determine its path and better understand what's going on, so you can follow it through the chemical reaction. Okay, radionuclides react chemically exactly the same as non-radioactive, but they can follow them because they glow, or they give off a signature, whereas the non-radioactive one doesn't, so they can follow it through and see what's going on. Okay, some medical, there's a lot of medical applications of radioactivity. I know, which sounds weird, because if you're exposed to too much radioactivity, it's going to cause medical problems. So you got to be, there's a fine line, I guess. But radioisotopes are administered to a patient, usually intravenously, which means they usually drink it. And then they look and they follow it. They see, you have to wait a certain amount of time, and then they go through and they look and see what's going on with that radio tracer. It depends on what's going on, but you can see we have iodine, which I talked about, iodine 131. Its half-life is 8 days, so in a few days it's going to be out of your system. But it's, again, to study if your thyroid's working properly. We have iron 59. Okay, that's for your red blood cells. We have a lot of, if you don't have enough iron in your diet, your red blood cells don't do very well. We have phosphorus 32, which works really good for your eyes, your liver, and if you have a tumor, it'll go to that tumor. Technium, okay, look at 6 hours and it's out of your body. Or 6 hour, half of it is gone, and if they don't give you much, it'll be gone pretty quick. And it says on the bottom too, isotope technically is actually a special isotope. Okay. But again, heart, bone, liver, lungs. We have thallium, which is in your heart and your arteries, and then sodium, your circulatory system. So those are some of the radionucleotides that they can basically have you drink, and then they go into your body and they follow them. Not always. Sometimes you have to get it through intravenous, but most of the time it's usually you drink it. And they follow it in your body. They'll run you through usually a CAT scan, CT scan, and they'll find it and see what's going on, whether your body's absorbing it, whether your body's using it, that kind of stuff. Okay. They can run you then what they call through a PET scan, positron emission tomography. It looks a lot like if you've ever had like an MRI. Okay. Here's an example of one with your brain. You can see normal. You can see if they have a little impairment, the dark part, that's a hole, you guys. And then look at somebody with Alzheimer's disease. So again, they had to drink something ahead of time, and then it went to their brain, and then they could read this. If you do a PET scan without that, you can't get these pictures, okay? So again, they use a positron, and the electrons collide to get that, and then they take pictures using that, but you can't use it unless you use that. So a compound labeled as a positron emitter is injected into the patient, and then they watch blood flow. They look for oxygen, they can look for glucose metabolism, other biological functions, whatever. And in your brain, it would be blood flow. Okay. And then if they have it labeled, then they can use it. Again, here's labeled glucose is used to study the brain. Why glucose? Remember, glucose is your fuel for everything. So if your brain's not using it, that's basically empty. And you can see the poor person with Alzheimer's has a very empty brain, which is pretty sad if you've ever known anybody that's gotten Alzheimer's. So again, you can use those radiotrons to do that. Okay. This will be our last slide. Okay. And the next, well, I just put this in there so we can finish the next time. But energy, we have nuclear reactions. There's a tremendous amount of energy stored in the nuclei. I talked about that a little bit. We talked about the bomb dropped on the Japan's on Hiroshima and Nagasaki. There's a huge amount of energy in there. One of the guys that actually helped develop the atomic bomb is Einstein. And it's because of first E equals mc squared, which I'm sure you've heard. But they used that to figure out how much energy they could get from the nuclear bomb. Okay. So again, we'll talk more about that next week. I just wanted to get the slide in so we make sure we get done next time. Okay. But this time, your assignments are all going to deal with half-life. And again, I will give you an example and stuff to follow.